Linux has a unique ability that very few operating systems in history have achieved. It scales gracefully across an enormous spectrum of hardware. The same core system that powers tiny single-board computers and decade-old laptops also drives the majority of the world's supercomputers, massive cloud data centers, and critical infrastructure. This isn't an accident, and it isn't just marketing. It's the result of deep architectural decisions, open development practices, modular design, and a philosophy that prioritizes flexibility and control. To understand why Linux scales better from old laptops to supercomputers, we need to examine its design principles, resource management, ecosystem, customization capabilities, and the culture that shapes its evolution. At the heart of Linux's scalability is its modular architecture. Unlike monolithic consumer operating systems that bundle tightly integrated components designed for a specific hardware profile, Linux is built around a kernel that can be configured, trimmed, or expanded depending on the environment. The kernel itself supports modular drivers, loadable kernel modules, and configurable subsystems. On an old laptop with limited RAM and a slow processor, unnecessary modules can be omitted entirely. On a supercomputer node with thousands of CPU cores and high-speed interconnects, specialized modules can be included to optimize parallel computation and networking. This flexibility allows Linux to fit into environments with radically different performance constraints without carrying excess weight. Resource efficiency is another major reason Linux scales so well downward to older hardware. Many Linux distributions are designed with minimal overhead. There are lightweight desktop environments like LXDE, XFCE, and others that consume very little memory and CPU time. Even beyond desktop environments, the base system itself avoids heavy background services unless explicitly installed and enabled. On an aging laptop with 2 GB of RAM, a carefully chosen Linux distribution can remain responsive and usable, whereas many modern proprietary operating systems struggle under the same constraints. Linux's process scheduling, memory management, and file system behavior are optimized for efficiency, and because the source code is open, performance bottlenecks are constantly identified and refined by a global community. At the other end of the spectrum, Linux's kernel is designed for extreme scalability in multiprocessing and distributed environments. The scheduler has evolved to handle systems with thousands of CPU cores. Its support for non-uniform memory access, NUMA architectures, allows it to efficiently manage memory across multiple processors with different memory latencies. Advanced I/O schedulers and file systems like XFS, BTRFs, and X4 are optimized for high throughput and reliability. In supercomputers, Linux can be customized to remove unnecessary components while enhancing support for high-speed interconnects like InfiniBand. The same core kernel that boots a Raspberry Pi can also coordinate massive computational clusters, performing scientific simulations or artificial intelligence training. Another key factor is configurability at compile time and runtime. When building the Linux kernel, developers can choose which features to include. For embedded systems and older machines, this means stripping away features that aren't required, reducing memory footprint and attack surface. For enterprise servers and supercomputers, it means enabling advanced capabilities like huge pages, specialized networking stacks, and fine-tuned CPU governors. This build-time configurability is rare in mainstream operating systems, which are typically distributed as fixed binaries with limited customization. Linux's ability to be reshaped at such a fundamental level is a major reason it adapts so well across hardware generations. The open-source nature of Linux also plays a crucial role in its scalability. Because the source code is available to everyone, hardware manufacturers, research institutions, and independent developers can directly optimize Linux for their needs. When a new processor architecture emerges, such as ARM, RISC-V, or specialized accelerators, Linux can be ported and optimized for it without waiting for a single corporation to prioritize support. This has allowed Linux to spread across diverse hardware ecosystems, from smartphones to mainframes. On old laptops, community developers often maintain drivers and patches long after manufacturers have stopped providing official support. On supercomputers, vendors collaborate with the Linux community to integrate cutting-edge hardware support directly into the kernel. Linux's driver model is another element of its scalability. Drivers can be built as modules and loaded dynamically, meaning that systems only use what they need. For older hardware, community-maintained drivers often extend the lifespan of devices well beyond their commercial support window. For high-performance computing systems, vendors can develop specialized drivers for GPUs, network adapters, and storage controllers that integrate tightly with the kernel. Because Linux is widely adopted in enterprise and research environments, hardware vendors have strong incentives to ensure robust Linux support. This virtuous cycle reinforces Linux's presence at both ends of the hardware spectrum. The package management ecosystem further enhances scalability. Linux distributions use package managers that allow users to install precisely the software they require, without unnecessary bundled applications. On an old laptop, a minimal installation can include only essential tools, conserving storage and memory. On a supercomputer node, installations can be automated across thousands of machines using scripts and configuration management systems. The consistency and reproducibility of Linux package management make it easier to deploy systems at scale. Administrators can replicate configurations across clusters or tailor installations to specific roles within a distributed system. Another important factor is Linux's strong separation between user space and kernel space. The kernel provides core services, while user space applications remain independent and replaceable. This separation allows different distributions to innovate independently in user experience, desktop environments, and system utilities without altering the fundamental kernel architecture. On older laptops, a lightweight user space environment can run on top of the same kernel that powers enterprise servers. On supercomputers, user space may be minimal, with no graphical interface at all, focusing entirely on computation and job scheduling. The kernel remains the stable foundation across these contexts. Linux's networking stack is also a major contributor to its upward scalability. It supports advanced routing, traffic control, firewalling, and virtualization features that make it ideal for large-scale distributed systems. In cloud data centers, Linux often acts as the backbone for container orchestration platforms, software-defined networking, and virtual machines. Its support for namespace and control groups enables containerization technologies like Docker and Kubernetes, which allow applications to be isolated and scaled across clusters. These same technologies can be used on modest hardware for development and testing, demonstrating Linux's consistent behavior across scales. Control groups, or groups, deserve special mention because they illustrate Linux's adaptability. Groups allow administrators to allocate CPU, memory, and I/O resources to specific processes or groups of processes. On an older laptop, this can prevent a single application from consuming all available memory and freezing the system. On a supercomputer, groups help manage resource allocation across thousands of parallel jobs, ensuring fairness and efficiency. The same mechanism works in both cases, simply applied at different magnitudes. Security is another dimension where Linux scales effectively. Its permission model, based on users, groups, and file access controls, is simple yet powerful. Additional frameworks like SI-Linux and AppArmor provide mandatory access controls for environments requiring high security. On an old personal laptop, a basic configuration may suffice. In a government data center or research facility, stricter policies can be enforced. The ability to layer security mechanisms without fundamentally changing the system architecture allows Linux to meet a wide range of trust requirements. The culture of Linux development also contributes to its scalability. It is not controlled by a single company with a narrow target market. Instead, it is developed collaboratively by individuals, corporations, universities, and research institutions. This diversity of stakeholders ensures that Linux evolves to meet the needs of hobbyists, enterprises, embedded developers, and scientists alike. Improvements made for supercomputing, such as scheduler enhancements or memory optimizations, often benefit everyday users. Conversely, usability improvements in desktop distributions can influence server management tools. This cross-pollination strengthens the entire ecosystem. Linux's adaptability to different processor architectures further explains its wide scaling range. It runs on x86, ARM, PowerPC, RISC-V, and many others. This portability means that as hardware trends shift, Linux moves with them. Old laptops with aging x86 processors remain supported, while cutting-edge ARM-based supercomputers can also run Linux. The kernel abstracts hardware differences through standardized interfaces, allowing developers to focus on higher-level functionality. Another reason Linux scales effectively is its minimal assumptions about hardware. It does not require high-end graphics acceleration, large amounts of RAM, or specific firmware environments to function. While it can leverage advanced features when available, it does not depend on them. This makes it suitable for reviving older systems that might lack modern capabilities. At the same time, Linux is quick to integrate support for new hardware innovations, ensuring that it remains relevant at the high-performance end. The file system landscape in Linux also demonstrates scalability. Lightweight systems can use simple file systems optimized for flash storage, while enterprise servers may deploy journaling or copy-on-write file systems with advanced snapshotting and integrity checks. Distributed file systems like Glusterfs and Kef extend Linux's reach into clustered storage environments. The ability to choose and configure file systems according to need allows Linux to perform well across storage-constrained laptops and petabyte-scale data centers. Virtualization and containerization technologies built on Linux have further reinforced its position at scale. Kernel-based virtual machine, or KVM, transforms Linux into a hypervisor capable of running multiple virtual machines efficiently. This capability powers many cloud platforms. On a small laptop, the same KVM feature can be used for testing different operating systems. Containers provide lightweight isolation, enabling efficient application deployment whether on a personal development machine or across thousands of servers. Performance tuning tools are another strength. Linux offers detailed monitoring and profiling utilities that allow administrators to understand system behavior at a granular level. Tools like top, atop, perf, and others make it possible to diagnose bottlenecks on both low-end and high-end systems. This transparency helps users optimize performance regardless of scale. The longevity of Linux systems also contributes to its scalability. Old hardware that might otherwise be discarded can continue operating efficiently with Linux. This extends the usable life of devices and reduces electronic waste. In research and enterprise settings, long-term support distributions provide stability for mission-critical workloads. The same underlying system can therefore serve short-term experimentation and long-term infrastructure needs. Community distributions tailored for specific purposes further demonstrate Linux's adaptability. Some are designed specifically for minimal resource usage, others for security, and others for scientific computing. This diversity allows users to select an environment that matches their hardware and workload precisely. No single version of Linux defines its capabilities. Rather, it is the ecosystem as a whole that provides unmatched scalability. The economic model behind Linux also plays a role. Because it is generally free to use and modify, organizations can deploy it at massive scale without prohibitive licensing costs. This economic scalability is crucial for supercomputing centers that operate thousands of nodes. At the same time, individuals can install Linux on old laptops without financial barriers. The absence of restrictive licensing encourages experimentation and widespread adoption. Automation and scripting capabilities in Linux are fundamental to scaling upward. Shell scripting, configuration management tools, and infrastructure as code frameworks integrate naturally with Linux systems. Administrators can automate deployment, updates, and monitoring across entire clusters. The same scripting capabilities empower individuals to customize their personal systems. This consistent automation interface across scales simplifies management. Linux's resilience under load is another defining characteristic. Its kernel is engineered to handle heavy multitasking, high I/O throughput, and sustained computational stress. Supercomputers rely on this resilience for continuous operation. Meanwhile, on older laptops, Linux often remains stable and responsive even under resource pressure. Its behavior degrades gracefully rather than catastrophically. Energy efficiency also contributes to scalability. Linux includes advanced power management features that allow fine-grained control over CPU frequency scaling and device power states. On laptops, this extends battery life. In data centers, efficient power management reduces operational costs and environmental impact. The same mechanisms serve both ends of the spectrum. Finally, the philosophical foundation of Linux emphasizes choice and control. Users are not locked into a single interface, update schedule, or hardware requirement. They can tailor the system to their exact needs. This freedom fosters innovation and adaptation. When hardware ages, Linux can be adjusted to compensate. When hardware advances, Linux can be expanded to exploit new capabilities. In essence, Linux scales better from old laptops to supercomputers because it was never designed for a single fixed context. It was built as a flexible, modular, collaborative system that prioritizes efficiency, transparency, and adaptability. Its kernel can be slimmed down or supercharged. Its ecosystem supports minimal installations and massive clusters. Its open development model ensures continuous optimization across diverse hardware platforms. Whether breathing new life into aging machines or orchestrating the world's most powerful computational systems, Linux demonstrates that true scalability comes not from targeting a specific tier of hardware, but from embracing variability itself.